Good morning, Boker Tov. So this is the final day of the conference that hopefully all the Israelis go to vote yesterday. I managed to vote for the first time since 1981. So there was something good came out of this election, I guess. So our first speaker this morning is Naftali Tishby. And I think I probably know him longer than anyone else, I suspect, in this room. Military. You know him since high school?
I think that Gil and you are more or less the same place.
Okay. My memory of him from the military service is you can point at any star in the sky and he would know what is that star. So he's a physicist by training and then has over the years moved to computer science, and he's at the interface between computer science, statistical physics, and computational neuroscience, and where he has reached a high level of distinction. And most recently, he received the Landau Prize in Computer Science and the IBT Award in Mathematical Neuroscience. And he's going to tell us today about this interface between neuroscience and computer science and statistical physics. Please.
All right. Good morning. Thank you, Moshe, and thank you for inviting me here. I mean, this is really a great honor, and I appreciate the large number of people who made it this morning after the election night, which is always, at least for me, a sleepless night. So I am actually going to slightly change the topic of my talk after hearing some of the lectures here and try to say something about the interaction or what I call the science or the basic science behind the artificial intelligence. Just as being more or less a multidisciplinary myself, I find it quite incredible. And when talking about the future of computer science, so you know, computer science was essentially born as, both the concepts of computation and information are, in a sense, abstract and detached from the physical sciences, or the natural science in general. This was really the main idea behind the computer science at the time, that you really don't care how things are implemented. There is an abstract notion of computation and an abstract notion of information, which are, and something computer science was born as some sort of an avant-garde science, which is really detached from the old style of physical sciences. And what I find quite incredible, at least in the last maybe 20 years, that somehow the impact of computer science on the physical sciences is really becoming more and more profound, and we already saw it here in the context of quantum mechanics and quantum computation and some other things, biology, computational biology, and so on. What I want to address, at least the first part of my talk, really this issue of computation in biology, or biological computation, or physical computation in general. I mean, what is really the interaction between the abstract models of computation, like Turing machines, finite state machines, stack machines, all those beautiful mathematical ideas that were developed behind computer science. But eventually, computers are physical entities, and living organisms are physical entities. And to the extent that computation is actually implemented in the real world, it's implemented in the physical systems. So we already heard about, how those computer science ideas really affect our understanding of physics. For example, yesterday from Dorit and others. But I'm more interested in the connection between computation, physics, and biology. Especially what I believe is going to be a dominant factor in the future, the interaction between computational science and brain research in particular, and biology in general. I mean, what do we mean by computation in biology and so on? So I'm going to essentially talk about three different topics. First of all, this notion of information, computation, and life, and a little bit just on a more abstract level. So we heard a lot in this talk from Amnon and from Sarit and a few others on the technological impact of AI. I mean, which is clearly a revolutionizing thing. I mean, it's a complete dream comes true to me, at least someone started to work on these things in the 80s, to see how many of the things, like, image recognition, speech recognition, language understanding, and so on. Some of these challenges that I didn't believe we are going to see implemented so successfully today. But what is really fascinating for me, at least, is that it also has an impact on the very basic sciences. And so I want to talk first about life, information, and computation. And just when you think about it, I mean, what do we mean by computation in a physical system or in a biological system? So there's really two completely separate entities or world, the abstract computational models. A Turing machine is a mathematical machine, and nobody, maybe except some toys in exhibitions, don't ever built a Turing machine. But it's really a very powerful paradigm, I mean, which essentially takes some sort of an input encoded by bits through some sort of a process which we call the computational model into an output, which I call it Y. But this abstract computation is eventually implemented in the physical world. Any computer is a physical device. In order to actually do this, when do we say that a physical device is actually a computer? I mean, is this a glass of water a computer? I mean, or can it be a computer? Or is my brain a computer? I mean, this is not at all obvious. But in order to actually talk about computation in a physical system, it's not just the dynamics of the evolution of the physical system, which is the topic of physics for many years, but what actually makes a physical device a computer is the ability to encode the input in the state of the physical system, in the initial condition of some dynamical system and so on, and then eventually so there's always this notion of an encoder, which essentially embed in the physics of the problem the actual input that I want to start my computation from. And then essentially, I let the physical dynamics, the dynamics of the system, with or without control of some sort, evolve the initial state of the system to some sort of a final state of the system. And then I need this decoder, which essentially maps the state of the physical system back into my computational model. And so there's always this decoder, these blue and red arrows, which are going to go through my talk. So essentially, what makes a physical system or a biological system a computer, or when we can actually talk about computation in physical systems, is the ability to encode our input in the system, control well enough the evolution of the system, such that actually the final state of something in the final state of the system, if not, it may be just, there's some sort of a partial decoding, like the kind of thing that we have in quantum computation. We don't really read the state of the system, but we perform a measurement which allows us to read something close or exactly the output that we're interested in. Now, it's really important to understand that to make this diagram commutative, in the sense that our computational model is really implemented by the physical system, is not at all trivial. I mean, that requires good understanding of both the physical system and the computational model. But of course, once we have this commutative diagram, we can use it in both ways. I mean, we can use the abstract computational model to make prediction on the physical system by reversing the decoder, for example, or on the same time use the physics in order to actually perform a computation. And we actually heard about this type of, the fact that we can actually build such commutative diagrams and jump between the abstract to the physical world is really and this is really what makes the whole thing so fascinating. Now, the physics of information, I mean, so I said already that we usually, and we heard in this meeting quite a lot about Turing and Shannon, which are, to a large extent, really important, really generated this information computation revolution that we are exhibiting. But actually, I think that the notion of information, at least, and actually also the computation, was born actually in physics. And I think it goes all the way to Maxwell. James Clerk Maxwell, the same one who is responsible for theory of electromagnetism and a few other things. So already in 1870s of the 200 years ago, this notion of how can intelligence interact with physics and essentially violate things like the second law of thermodynamics, which Maxwell quite ingeniously thought about, and then later on was called Maxwell's demon. If there was a creature that will actually observe the molecules in a vessel and separate between the fast and the slow molecules just by measuring their velocity, he could actually generate something which I believe he really put the finger on both the notion of information and the interaction between information and thermodynamics and entropy already there. So in my opinion, it's not only my opinion, I mean, it's quite a dominant view today. It was really James Maxwell who invented the notion of information and really realized that there is some deep connection between measurements, information, and thermodynamics and irreversibility and many other things. Now, slightly later, I mean, the same idea was developed into something which Szilard, another physicist who was responsible for many interesting things, but among other, he was one of the leaders of the Manhattan Project. So in the 20s already, he took, of the 20th century, he took the idea of Maxwell's demon and turned it into an engine, which we now call the information or Szilard engine or information engine, which essentially takes the idea that I can actually perform a measurement on the real world and turn information into work. Or if you want, information measurements about a velocity or a position of a molecule, and if I know how to measure it more or less reversibly without losing, I can actually turn this information into useful, valuable thing like mechanical work. And this was, again, one of those fundamental connections we can understand better, much better, between the abstract notion of information, which was only later by Shannon was formulated, and the classical notion of energy and work. And to a large extent, science was about energy and matter until the middle of the 20th century. And due to Shannon and Turing, slowly moved from interest in energy and matter and transformations of matter to what we call now computational information as the main objects of science. And this one, equations like this, which really connected to information and energy, really tell us, okay, you can't really separate these two things. And eventually, what is really interesting about this Szilard engine, this demon, which observed the position of a molecule in a vessel, and by knowing if it's on the left or right of this vessel, I can actually use thermal baths to generate useful work. He also, these two people, Maxwell and Szilard in some sense, really also pointed out to me, again, I'm not the only one who thinks like this, the basic notion of an organism, of a living organism. So not only they invent the concepts of information, but they told us what is the simplest possible life. In some sense, anything which is able to turn measurements of observation of the environment into useful or valuable, future valuable entities like work or like any other kind of value, which can be money or offspring or whatever, is in my definition and many other definitions, is really the basic, simplest possible concept of a living organism. This is an organism which actually has a perception, a sensing of 1 bit per cycle, a memory of 1 bit, which remembering which side this particle was, and then an action of 1 bit, deciding where to put the mass on the left or the right of this tube or this device, and eventually generate work by turning this information and the heat in the heat bath into useful work. This is life. And what is really nice about it, these two abstract concepts of information, observations, memory, and acting really tell us, okay, what is really the minimal requirement from a living organism? And that's something, by the way, the biologists hardly ask at all. I mean, if you ask them what is life, they usually talk about reproduction and metabolic exchange with the environment and other things. They don't talk about information. But information and this notion of observing, remembering, and acting is really the fundamental aspect of living organisms. So again, Maxwell's demon with this construction of Szilard is really telling us that the basic ingredients of biology is the ability to interact with the environment, sense it or measure things in the environment, and turn it into valuable behavior in the future. Now, if you buy this, again, this notion of the connection between information, work, and memory and computing in some sense is really answering one of the most fundamental questions in biology. What is life? How can it emerge spontaneously, for example? What is the chance of finding life in other places, entirely different chemistry, entirely different environment, and so on? What is really the fundamental aspect of what we call living organism? Now, for me, this is a very exciting connection because it brings together exactly those fundamental concepts of statistical physics with the fundamental values of information, with these concepts of information and control. And in some sense, we now know, and this is, again, a large part of my own work, we can think about an organism, let's say this red here on the side, on the left, as an object, a system which is able to turn past observations through its senses into valuable behavior by some sort of prediction. So again, so our model of computation is very much based on a model of life, if you want, is very much based on these two concepts that I mentioned before, encoding the information from the environment through our sensory systems, which is this blue elements here, are observed entities in the world, processing it in the sense that I have to remember some things from the past, but not everything. Most of what I sense, I don't remember, and I don't preserve, in a way which allow my actions, which are some sort of another interaction between my memory and the world around me, in a way which would be valuable. So this is life, turning past information into valuable future. If I can do this, according to this definition, the very fundamental definition of a living organism is not chemical, and it's not biological, it's actually information, theoretic, and computation. Now, this abstract definition of life is also at the core of what we call artificial intelligence. So essentially, I take this notion of valuable rewards, or expected future reward, as the basic driving mechanism of what we now call machine learning and AI in general. I mean, sense the environment, and we usually use it within this feedback loop that we call sometimes reinforcement learning, or I like to call it a perception action cycle. And our brain is, to a large extent, very much its main task, and also its main anatomy, if you think about it, is exactly about, most of the dorsal part of the brain is about sensing and processing sensory perception, sensory information, and exactly filtering out the relevant from the irrelevant, whereas the frontal part of our brain is essentially planning ahead, making decisions, plans, and so on, thinking about the future. So this encoding, decoding, memory, and computation is aimed at one thing: exploit the predictability of the environment for useful actions and behavior which eventually allow you to survive. Okay, so this is nice because here we actually marry together some fundamental aspects of computational information, to really understand maybe the core or the key question in biology. And what is nice about this type of definition is it's the same definition exactly can apply not only to living organisms, but to artificial organisms or to artificial intelligence system or whatever you want. It's the same definition, the ability to exploit information from the past through some sort of sensory information in order to behave effectively. Now, I've been playing with this type of idea for many years. And essentially, okay, so this is my caricature of what the brain is doing. It's essentially taking selective sensing of the environment. So the world is this chain of colorful events. It's, of course, a very crude model of the environment, but that's what we all. We all sense those things which are more or less stationary. And the question is, how much of this observed past we actually need to keep in order to interact with the future in a valuable way. And, of course, a condition for this to work is that there is information in the past about the future. And this is something which we call predictive. So the environment must be predictable to some extent in order for life to exist at all. Because if there's nothing in the past to tell us anything about the future, there's nothing to exploit. So a very fundamental concept here is essentially this, what I call the bottleneck or the information bottleneck, is how to extract the minimal information from the past, or the minimal information about the future, which the past allows us to extract, and the ability to extract bits about the future from the past is a precondition, is a necessary condition for survival of organism. Okay, so that's what is nice about this, is that we can actually calculate it, we can actually formulate this mathematically. Again, using this abstract notion of information, I don't want you to get into these equations now, you can actually calculate what is the optimal, the absolute information theoretic optimal bits of information from the past that can be useful in the future, given some properties of the environment. And eventually, the evolution of a biological system is going to make the environment more predictable. You know, we build houses in order to protect ourselves from the unpredictability of the weather. We keep our social interactions more or less predictable in order to survive, and so on and so forth. I mean, so society, culture, everything that we know about biological systems is about turning the environment to be more predictable and therefore allowing us to plan ahead in a more and more sophisticated way. So one of the things that we have been doing is formulating this trade-off between how much information you need to extract from the environment, which is valuable in the future, into one very simple variational problem: minimize the information that you sense from the past under a constraint on information that you have about the future. And this can be solved and computationally calculated in many, many cases. So it's really a very simple notion. It turns out to echo, to be connected to many other different things, like, you know, minimal sufficient statistics in statistics, or minimal work required in a thermodynamic system, and many other things, which somehow seem to be encapsulated by this single principle: minimize the information from the past under some constraint on information in the future. And there's, in this, what I call an information plan, there's this very nice trade-off, which is this black line. Given the environment, this is the best you can do. Anything below this line is achievable by some types of system. Anything above this line is unachievable by anything. So not even a very clever alien for space cannot be above this line, given the same environment. This is what we call an information theoretic bound. What I'm going to show you now is that not only we have this computational framework that allow us to divide between achievable and non-achievable organism in that sense, in some environment, but that some of our AI systems, in particular deep learning, actually achieve these bounds in some interesting ways. So we are up already in a point where artificial intelligence is reaching this information theoretic bound sometimes. And I believe this is really the secret behind the success of things like deep learning. But of course, what makes me so excited about it is that it's the same principle exactly that governs biology, and that's why I look at real biology, real brains, real neuroscience, in the same way exactly that I look at artificial system, and in the same way exactly as the same principles apply in both cases, and this is really the beauty of it. So in a sense, okay, I could get more into it. So again, what I just want to emphasize this one thing. So in order for, this is done with Bill Bialik and Nili many years ago. So there's this fundamental characteristic of any environment is how much information in some window into the past is actually predicting anything about the future. How many bits are there that I need to remember will actually tell me something about the future? If you think about it, this is really the fundamental question of science and of intelligence, or whatever, intelligence both in the military sense and in the AI sense, whatever. So we take two windows of some process, let's say stocks in the stock market, and look how much of the current behavior or the past behavior is telling us about the future. And what is really surprising, and this was really it led to many, many different papers. I don't want to, essentially just calculating this mutual information between past and future into different windows, as I said before, is actually putting a bound on the complexity of an intelligent behavior, because if anything that I can do which is intelligent depends on my ability to extract knowledge from the past or the future. And if I ask you, how much do you think information there is, let's say, in the last 1,000 years, which is actually valuable for our futures? Of course, this is a very stupid question, because it's not a stationary process, and it's not very easy to, but that's what we actually try to teach in schools. I mean, exactly the things in the past which are going to be valuable sometime. But on the short term, assuming some sort of stationarity of the environment, let's say when I talk about language, when I talk about any intelligent behavior in some more or less stationary environment, this actually can be answered exactly. And under some assumption about stationarity, the surprise is that the number of bits in the past which are actually predictable in some sense, they actually give me some information about the future, is a tiny fraction of the actual entropy or the actual complexity of the past. It actually behaves for finite dimensional systems like log of the size of the window. So it's very, very tiny, log t over t. The entropy grows like t, but the predictive information grows like log t. So it's a tiny fraction, log t over t, which is really important. And if the environment is really complex, so it's not a finite dimensional system, it can grow like a power law, like square root of t, or something like this, power law smaller than 1. So this really was somewhat surprising. But if you think about it, this is actually the reason why living our limited brains, which are still limited, can actually cope with the complexity of the world, because most of the things in the world are not important. So the main task of a brain is to filter out those informative bits. Okay, so again, this actually put us into this very nice picture, which I like to show, but it's a bit complicated to explain. So if the goal of an organism is to optimize the future value, whatever it is, money, offsprings, whatever you think about valuable in the future, given the cost of existence, I mean, the metabolic cost, the energetic cost, the financial cost, whatever it is, the computational cost. So there is a very complicated relationship between the cost of the past experience existing until now and the value. Both of these functions are extremely difficult to calculate. But what essentially, just by mimicking the structure of information theory, I can actually turn the future value into bits. What is the minimum number of bits that I need to know about the future in order to achieve a certain goal? Let's say to get back home today, or whatever, to finish this talk. I mean, so this is something I can quantify and can calculate it, and it looks very much like rate distortion theory. The minimum number of bits about the future required to achieve a certain expected value. And the same I can ask about the past. What is the maximum number of information that I can gather from the past in terms of bits that at a certain given cost? The cost of sensing, cost of memory, cost of computation, whatever it is. And these two functions, the blue and the red, which are again related to this encoder-decoder issues, once I have these functions, I know that the predictive information of the environment is going to govern the ability to actually achieve this cost-value trade-off. So this complicated physical question, the physical cost of my experience and the future value of my behavior actually turned into completely purely information theoretic bounds. And that's really the beauty of it. So I turned biology again into information theory. Okay, so now I want to switch and go back to the title of my talk. I mean, talking about deep learning. So I'm sure that all of you know that artificial intelligence, which we historically associate with Turing in the 50s, the idea that our brain is not more than a Turing machine, and therefore we can actually mimic it by computer, and mimic every aspect of our intelligent behavior, is of course started in the 50s and was for about 30 years, was essentially based on logic and lookup tables, what we call expert system. I mean, the idea was essentially, okay, tell me how you understand speech, or tell me how you walk, or tell me how you see, and I'll program it, and that's it. I mean, to ask an expert and program his knowledge. Of course, this essentially failed. I mean, for anything not entirely trivial. In the mid-'80s, when I more or less started to get interested in these things, there was a big revolution, and we moved from logic-based systems, combinatorial systems, to statistical systems, and essentially say, okay, we can't really ask an expert because no expert can tell me how do you see, or how do you walk, or how do you understand language. Let's learn it from examples, essentially, from data, using essentially the principle of statistics. And it's actually quite amazing that until these days, more or less the late 80s, statistics and computer science it didn't marry very well. Actually, when I wanted to come back to Jerusalem in the late 80s, early 90s, I was asked by many distinguished computer scientists, why is this thing, which we now call machine learning, statistical algorithms for doing AI, why is this part of computer science at all? I mean, and some of them thought it should be either in physics or in electrical engineering, but not in computer science. I mean, we talk about logic and computational bounds, and now you're trying to do statistics. We all know that this was essentially wrong because this marriage of statistical regression, curve fitting, with what we mean by real data with efficient algorithms, actually a very productive and a very powerful thing, which led to what we now call machine learning. But at the same time, in the mid-80s, there was another idea, which essentially mimicked the brain, or mimicked the computational elements of the brain by some sort of a crude model of what we call neurons in the brain as logical devices, which are essentially these linear threshold gates. Something like those things essentially mimic the connectivity of neurons in the brain by a linear threshold function, essentially take the dot product of some weights with the input, push it some sort of nonlinearity, and this is our basic computational element. And this very crude implementation of a neuron, the McCulloch-Pitts neuron, which is really a very simple-minded thing, was born in the 80s, or actually was not born in the 80s, was born in the 40s, and had many historical transformations. But eventually, the idea of a neural network, stack these things together in layers, some layers, few layers, many layers, was already born there. And we already knew then, at least people who came from physics, that there's something very interesting about this large-scale learning. I mean, when we talk about many neurons, suddenly the rules of statistical physics take over again, and we can talk in terms of very few variables, in terms of millions of possible parameters which are there. There are only very few variables that really control the behavior. And that's an idea that comes from statistical physics. I mean, we know that the air in this room is completely dominated by very few numbers. Before I enter the room, I need to know essentially the temperature, the pressure, and the chemical composition. That's it. If you tell me this, I know that I can enter safely here. The fact that there are 10 to the 26 molecules moving around is really completely irrelevant, as long as I know these 4 numbers, or 5 numbers, or 10 numbers, or whatever. Something very similar happens in these large neural networks, and that's, again, one of my views of this matter. So essentially, the miracle of deep learning is that by stacking these McCulloch-Pitts neurons in many layers and adjusting those parameters and train them in the most naive way, just by essentially gradually, by gradient descent or stochastic gradient descent, adjust all the weights, which is something which we call backpropagation of error or error backpropagation, just layer by layer adjust the weights, suddenly those multi-layer, very naive machines with some bag of hacks and tricks like convolutions and things like this, which I don't think are very important. They're important because they save a lot of computational time eventually, but fundamentally they're not important. Eventually, I'm able to do essentially optimal, human-like performance in terms of object recognition, is it a dog or not a dog in my image, or is it me in the picture or not, and so on, and understanding speech and so on. So how is it done? So this is, and again, it's not only the surprise that these things work so well, but they seem to violate some of our basic understanding of statistical models. I mean, more parameters don't hurt us. We don't seem to overfit very easily in the sense that usually we think that the size of data should scale with the complexity of the model. Here, the complexity of the model, and at least formally, the complexity of the model can be very large with relatively small number of data points. And it still works. Not only it works, when I add more data, I actually get better. Only 5 minutes. OK, that's impossible, but never mind. So what we did is essentially, again, exploit this notion of encoder and decoder in a very fundamental sense, like what I told you about the basic understanding of computation. So I think about the information that is encoded in each one of the layers and the decoding from this information. And this, again, using the principle that I told you, I can actually find what is the optimal way of doing it for a given data. And the main theorem or the main result that we have, the encoder and decoder of a neural network actually eventually pushed by this algorithm of stochastic gradient descent to exactly this optimal limit. That's, of course, it sounds like unbelievable, because why should it? And of course, so much of my work in the last 5 years maybe with a lot of people is actually to show, and I'm just going to flash this movie to you. This is again the information plan, information about the past, information about the data if you want, information about the label. And you see that the evolution that we actually play with in the stochastic, in the way we train those networks, is really pushing all the layer by layer, into this limit. So essentially the message I usually take home is that if you look at this, 2 variables only, how much information each layer remember about the input data, and how much information it's actually giving me about the prediction label, the prediction of the label, everything becomes very simple. The evolution of those layers, again, in the large scale limit, when I talk about very large problem, because it's some sort of a thermodynamic limit, the evolution of the layers through the training goes through these trajectories, which are really quite interesting, and there's a lot I can say about them, but I don't have the time now. They first go from A to C, which is some sort of memorization of the data. I just memorize everything. And then I start to do this selection, or what I call forgetting, or filtering out the irrelevant information from C to E. And eventually I push the last layer to a very good point that it actually remembers about the data exactly 1 bit, which is what I need in order to predict the label. But all the previous layers somehow, in a hierarchical way, find intermediate representations which seem to capture more and more information about the data, but still reduce the complexity. So this is some sort of hierarchical compression or forgetting of the previous data, which is really dominating these models. And of course, there's a lot of debate in the literature today among linear theorists and among other experts whether this is always happening or this is really the typical behavior. What I'm saying is that you have this type of trajectories. Look at only these 2 dimensions. Information that each layer has in the encoder and information that they have in the decoder. And these 2 numbers really tell me the main story, and when I change the size of the data, I may get to the left side here where essentially you get some sort of overfitting or forgetting. The forgetting is not very effective. We understand this pretty well mathematically now with a lot of interesting detail, which I'm not going to get into. One of the main surprises of this understanding is that more layers is actually more effective computationally. So with more layers, you see here the same problem land with 1 hidden layer up to 6 hidden layers. You see that the number of epochs, or the time that it takes to converge to a good solution, actually goes down with the number of layers. And the reason is that those layers actually help each other. They push each other. The fact that I'm forgetting from fewer and fewer with more and more layers is actually effective. It's like a train with more engines that really push it faster. And that's actually a lesson for the real biology. And the last chapter of my talk, which I'm obviously not going to complete, is how is this related to real biology? And what is really missing? So in that sense, if I'm right, deep learning in this particular way of many layers of neurons trained by stochastic gradients and some data, under some conditions, which have to be specified, can achieve this optimal information theoretic limit. In that sense, they can be optimal machines. So they not only compete with biology, they can beat it in many cases. And again, when we look at what actually happens, let's say in our visual system, in let's say human visual system, there's also this hierarchical organization with some sort of many layers. It's not exactly in the same form. There's a lot of feedback. There's a lot of mechanism there. But we actually see, and the same is true about language, we begin to see the correspondence between this hierarchical organization of the layers in deep learning and the organization of the biological brain. So I'm going to skip a lot of what I wanted to say about the hierarchy in the brain and how is it related. But eventually, what is really nice about it is that we seem to be able to put on one finite and clear set of principles, which are computational, information theoretic and computational in terms of time that it takes to reach a solution. Both artificial intelligence and biological intelligence on one setting, and begin to understand the hierarchy of representation in the human brain in the same way that we begin to see inside this black box of deep learning, we understand the organization. So it's again, it's a wonderful story because this abstract concept of computation and information become a very clear fundamental principles of understanding physical and biological systems. And I wanted to say a lot about the discrepancies between AI and biology, but let's leave it for another talk. Okay, thank you very much.
Thank you, Tari, for a wonderful... Can you hear?
Yeah.
For a really wonderful talk, but I'd like to take the position of a conventional, old-fashioned computer scientist who doesn't take any of this with skepticism. On the contrary, one of the problems that people like me have with deep learning is the fact that there's no method yet for actually verifying that they have properties that you want of them. So here I'm not talking about the biology, I'm talking about your cats and dogs, or designing deep learning networks to do something that we're building. And so the problem of verification of these deep neural nets. What is your take on that? I mean, there is exciting work, some of it done by Guy Katz and other people in your institution, but what's your take on the future of that?
So I'm not sure what exactly you mean by verification. So there is a notion of generalization, of course. I mean, how much we do, how well we do outside the training, and which is, of course, under control in some sense. I mean, either theoretically or empirically, in most cases, by some sort of test validation and so on. Verification of the fact that it is optimal, that's what you're saying.
No. Even saying that, this neural net will correctly identify dogs, 90% of the time.
Okay, so there are many issues which I didn't get into, like, the adversarial examples and the robustness and so on of these systems, which are very important, but that's what I could say in 10 minutes. But, of course, how much the whole thing is really robust and stable, and obviously our biology seems to be a lot more robust, although it's not. It's an illusion. I mean, essentially all those adversarial things which we do with the artificial neural networks confuse most people as well. I mean, maybe slightly different adversarial things, but we are very susceptible to illusions and to optical illusion, to language illusion, and so on, because of this compression. So this compression is really fragile, and to make it robust is a very interesting issue. I'm not sure this is what you mean, but maybe we should take it offline. I mean, what do you mean by verification? I'm not clear about it. More questions? Yes.
Can you say in 2 sentences what is the basic difference? What is the basic difference between deep learning systems and biological?
Okay, so there are many differences. I mean, actually, so first of all, at least deep learning are feed-forward systems. I mean, the backward is done only during the training, but once it's trained, it's a feed-forward. And we know that our brain has a lot of feedbacks. So actually, one of the things that we are doing now, and of course, for example, one of the criticisms that you hear from brain scientists is that all this idea of error backpropagation is not biologically plausible, and so on. So one thing that this information bottleneck I detailed you that you don't need at all the backpropagation. You can actually train every layer by optimizing the encoder and the decoder just from the previous and the next layer. So that's something which we do now and seem to work better than backpropagation. So that's, again, so there are many, so feedback, a recurrent network, we're not talking about a few layers, there are many reverberation of information. There's a lot more robustness. I mean, there's obviously clear that biological systems are more robust. Why they're more robust? It's a good question. It's not really clear. I think they're more robust because there's a lot of stochasticity in the system, which makes it noisier, slightly less efficient, but much more robust to very small changes and so on. And there are many other things. I mean, but the fact is that this deep learning, by surprise, by the way, nobody thought that this is going to happen, actually theoretically, in some cases, achieving an information theoretic optimum. And that's something which you can't beat. The question is whether biology can do it or not. Of course, once we talk about things like behavior, reinforcement learning, planning, and things that actually go beyond just like classification, or maybe Gal is going to talk about it, I don't know. This is how we train robots, how we plan to train, how we do reinforcement learning and things like this. This is all open issue. It's not really clear, and we are not yet in any good understanding theoretically what's going on there. But it's combining optimal control with partial information. These POM-DP type of models are very hard computationally and very hard to implement biologically. But there are many things. And I don't want any of you to get the impression that deep learning is as good as biology. I'm just saying that under certain conditions, it can be optimal information theoretically, at least, and this is also interesting. All right, I think we stop here.